Okay. Yeah, I guess it's a good time to just begin. So we're happy to have Chia-Hsien Cheng from the UCLA and moving to UCSD, and he'll give us some introduction and some recent and updates on research recent work on amplitudes meeting LIGO. So please take it away, Chia-Hsien.
Okay, first of all, thank you for the organizers for the invitation. It's a great pleasure to visit India, first time, even though it's only virtually. Hopefully I'll physically visit India at some point. So today I'll talk about amplitudes meet LIGO, and this is a relatively new direction in the amplitudes community. My idea today is to give you an overview about this subject, and also personally find it very interesting because you can talk to people from the classical GR background. So today my talk will be based on this recent work from last year and also this year with my fantastic collaborators. But there will also be some important papers where we build upon our ideas and also put it here, and I'd like to bring to your attention. So I'm sure you heard about from the lectures that about this asymmetrics program. So the basic idea is that in the standard quantum field theory. Oh, by the way, I should say, please interrupt me if you have any question. So for this asymmetrics program, we usually start with some basic physics principle, like locality, unitarity, and possibly with some symmetries. For example, like gauge invariance, etc. And then we write down the consistent local actions. And from the local actions, we use Feynman diagram to calculate amplitudes. However, there's a huge redundancy in the local actions. So let me just give you a very simple example. Suppose I have a free field theory. Oops. Suppose I have a free field theory. I can make this Lagrangian looks arbitrarily complicated if I do a simple real field redefinition. So this Lagrangian will simply looks like it has like 3-4 point interaction. But when you calculate all the Feynman diagrams, you add out all the contribution, you'll find out that the amplitude is identically 0. So that means the local action has a lot of redundancy, but those are not physical. So the idea of asymmetrics program is actually want to jumpstart from this basic physics principle and move from here to directly get the physical final answer. So one elementary application about this amplitudes is that we can use the amplitude to parameterize what physical degrees of freedom are in your theory. So for example, you can take the simple, just based on kinematics. For example, for 4-point, we have S and T parameters. And in the case of spin, you can also use your data group to constrain your data. So from here, you can parameterize what the freedom you have in your theory. And one simple example is in the case of gravity. So I believe this is what Laddha talked about the other day. You can find out what the three parameters you have, starting with the counting of Einstein-Hilbert action. You can just with R squared, R cubed, L dimension operator, etc. in various dimensions. So another application of this very basic idea is the so-called standard model effective field theory, which is standard model plus higher dimension operators. So for example, we can have dimension 6 operators. Now, normally what you need to do is you write down all the possible operators, but it might be very complicated to see what are actually independent ones, because different operators, they can be related by integration by part or field redefinition. But the amplitudes way of doing that, especially starting from this parameterization, give you an invariant definition about what are the possible parameters. In this context, we're going to see that the two-body, the classical effective potential, or the ADN Hamiltonian, you can also apply eccentric. So you're gonna see that shortly that is basically a one-line argument simply because the 4-point function is given by S and T parameter. We know exactly what are the degrees of freedom in the classical effective potential. So this is just one tiny corner about the application from on-shell method that we can see easily like what are the degrees of freedom in your theory. Okay, so that's all I want to say about the general thing about S-matrix program. So the next topic that we want to make connection with is gravitational waves. Oh, I see there's some time delay on my screen. Good, okay. So I'm sure you all heard about gravitational waves from the discovery about LIGO and VIRGO. And I'm not sure if this audience are interested in phenomenology or more toward formal interests. But here, let me just give you a brief motivation about why our friends in LIGO are interested in what we're doing. So a basic event in LIGO is like the following. You have the binary system. This could be, say, black holes or neutron stars. So in the very beginning of the event, these two bodies are relatively far apart. So the distance is long, so the gravity is very weak. You can use phase-space approximation. And also because they're far apart, so you can take these two particles basically as point particles. And you have some gravitational wave signal, and that is the so-called in-spiral stage, which is actually the majority of the LIGO signal. So in the very end of this in-spiral event, the two bodies, they become close enough to each other. And so, for example, the two black holes, the event horizons begin to touch each other. And this is a case where the gravity becomes strong. You can't use any perturbation theory, and the only reliable theoretical tool here right now is only numerical relativity. And that's like this, the short instant, that's the so-called merger. So after these two bodies merge together, you basically have a blob that's vibrating. And this is the so-called ring down phase. So in this case, you can also treat this blob as a black hole with some perturbation, say from the standard quasi normal mode. And this is so-called the ring down phase. So these are the basic 3 stages in the gravitational wave event. So this is a very theoretical signal. And of course, in the real world scenario, that's not what's happening. You basically have a lot of background that your signal is like buried inside this background. So our friends in LIGO and VIRGO, basically what they do is they take this measurement and try to compare with some different waveforms, the original signal. And in order to do that, they need to have to saturate the parameter space of all the possible waveforms. So the parameter space, basically what you have is a mass of M1, M2, like the initial radius R, for example. So you need to generate lots and lots of waveform. So this is possible to do using numerical relativity. However, the numerical relativity on one hand is very nice because it tells you from in spiral to the merger where gravity is strong and also all the way to bring down. But the downside of that is in order to generate this entire event, even on a supercomputer, a single event could take a few months. So in order to generate a lot of waveform, it's actually not practical to using just numerical relativity. So a more practical approach is to use a combination of analytical and numerical data. And this is famously what this effective one-body Hamiltonian models, or sometimes called EOB models. This is by Thibaut Damour and Alessandro Buono. So basically what this model does is they take the data from various stages, for example, some perturbation data from in spiral, and they combine with some numerical relativity, and that we produce a waveform that's comparable to numerical relativity. So for the discovery of a gravitational wave event, this is probably enough. But of course, eventually for LIGO, want to get higher precision, want to test about Einstein gravity. So in order to do that, we need more analytical control, and we want to bring this model to higher precision. So the requirement for that is we need more analytical data toward the input of this waveform model. So this is a place where the LIGO people, they're interested in more precision calculation. So the question then is, how much can we do? How can we help? Okay, so the basic question is, do amplitudes have enough information for bound states? So remember, when we start learning physics, bound state is actually the first system we learn about, for example, in Newtonian physics. And even when we go to undergrads, when we learn quantum mechanics, we also started with some hydrogen atoms. But as we move on to grad school and we learn more about quantum field theory, we sort of just more or less forget about bound states. However, this is a very basic physical system that definitely deserves our study. But the reason that we don't talk about bound state that much in quantum field theory is that the bound state, in some sense, they're sort of non-perturbative from scattering point of view. Because from scattering, the basic states we prepare are plane waves from the infinity. However, for bound state, they are definitely the radial wave function. Those are definitely very far from plane waves. So for example, let's just study the most well-known example of the hydrogen atom, comprised of the electron and proton. So imagine if we want to study this from amplitude's point of view. So the question is, how would you do that? So one way of doing that is we can study the corresponding electron proton amplitude, this 222 amplitude. And in certain limit, the amplitude is given by dominated by this diagram. So if you have the full control about the non-perturbative amplitude, then in this case, you can try to resum over these dominated diagrams. So once you resum these dominated diagrams, what I find out is actually that the amplitude actually develop a new pole, which is not present in your original states. And these poles correspond to the bound state coming from this electron and proton. And you can actually read off the hydrogen atom spectrum from these poles. However, another, actually a more low-bar way of doing that is to say, let's just do what we do in undergrad mechanics. So in undergrad quantum mechanics, what we do is we solve the Schrödinger equation. The inputs here are the Hamiltonian, which has a standard kinetic term plus this potential. So the potential to lowest order will be the Coulomb potential. And of course, you can add more QED effect by adding more higher dimensional corrections. However, once you have this effective potential, all you need to do is to solve the Schrödinger equation. And then, so once you have this effective potential, you don't have to know about the underlying quantum electrodynamics. The photons are integrated out. And so solving this bound state wave functions, the spectrums, is relatively simple. So we can turn this question around by how do we learn learn about bound states from amplitudes. So using the second idea, we can turn this question around and say, in order to understand from amplitudes to bound states, the connection might not be that straightforward. However, if we can start from amplitudes and we can learn about what is the corresponding effective theory or the effective potential, once we have this connection, then we can study the bound state much easier, because all we need to do is to solve either the Schrödinger equation for the case of hydrogen atom, or in the case of gravitational binaries, we can study the classical equations of motion. And because we already integrated out the complicated underlying GR effect, so these the classical equations of motion are simply some underground mechanics, which you can easily hand over to your LIGO friends, and they can input into their waveform models. So that's the approach we're gonna take in this program. And there's some pioneer work done by Goldberg and Rothstein on the original EFT formulation, and some later application which try to connect amplitudes with effective field theory by these two papers. So the goal here is we have so much understanding about the scattering amplitude, and we have powerful tools like double copy, generalized unitarity. So the goal here is to apply these powerful tools and to connect, to bootstrap what's the corresponding effective action. And we can use that to study binaries. And of course, GR is a very mature subject. So there we have a lot of understanding about what's the corresponding the dynamics of this binary. So in order for this to be successful, it's actually important to build a systematic program such that we can simplify the GR calculation in a systematic and scalable way. So that's the idea of this program. Okay, so that's the part of basic introduction. And I don't know, maybe this is a natural place to start if there's any question. Okay, I don't see any questions. So let me move on to the next part. So let's discuss with some slightly more details. So the basic object we want to study for this bounded binary is we want to study the corresponding scattering amplitude, the 222 amplitude, or a 4-point amplitude. So in the simplest scenario, let's just consider two scalars, two massive scalars. A 4-point amplitude, as we know, it has the S and T parameter. So the S parameter in the center of mass frame corresponds to the total energy, which, which is related to the velocity of this binary. The T parameter is related to the momentum transfer. So Q squared is T. And in the real space, Q is the 1/r, where R is the impact parameter or the orbital size of this binary system. So in this system, we have several parameters. We have three-dimensional parameters: G Newton, the momentum transfer Q or 1/r, and the mass. And we also have velocity. So from the first three-dimensional parameters, you can form two-dimensional Laplace ratios. The first one corresponds to Gm over r, and this is roughly the same as Schwarzschild radius over r. So you can view this parameter as a parameter corresponding to GR expansion, or the finite size expansion coming from the gravitational radius. The second one is coming from quantum correction. So this is Q over M, and in real space, this is 1 over mr, which is proportional to 1 over L, where L is the orbital angular momentum. So if you remember that the angular momentum, they're in the unit of h bar. So this numerator is actually h bar, which is set to 1. So this parameter corresponds to quantum correction, or say differently, this 1 over m is the de Broglie wavelength. So this de Broglie wavelength over the orbital size, and this will be tiny in the macroscopic system. So the final expansion parameter is v squared coming from velocity. So in the typical scattering event, of course, this v squared corresponds to s parameter. S is independent from the t parameter. But for the case of bounded orbits, like circular orbit, we know from VIRGO theorem that v squared is of the same order as Gn over r. So it means for bound states, these two are non-independent parameters. So these are the basic parameters or the expansions we have in this system. Important conclusion here is when we say scattering, what I'm interested here are the classical scattering. Classical scattering phrased in this language correspond to Q over M being very small. And we know Q is proportional to T, and the mass is roughly S. So that means for this scattering in the classical regime, that it coincides with the forward or the Regge limit. So from this analysis, now we can write down what are the possible expansions for our potential. So the potential, we have the Newtonian part, and the corrections come in two different ways, either as Gn over R from G expansion or the velocity expansion. So there could, in principle, be a third expansion, but this one corresponds to quantum effect, which we are not interested in here. So in the GR community, this G expansion is called post-Minkowskian expansion. And in field theory, because it's simply expanding in G, we simply call it perturbation theory. And the V expansion in GR is typically combined with G, because in bound state, as I said, these two are of the same order. And this will be a so-called post-Newtonian approximation, which combine these two expansions. Okay, so let me give a brief summarize about what we know so far about the two-body effective potential in the case without spin. So you can expand this potential either in G expansion, which correspond to this different horizontal row, or in terms of, for a given G expansion, we have different order in velocity. So the standard post-Newtonian approximation, the leading order is given by the Newton law. And this is way back in several centuries ago. The first GR correction could come in two different places. Either we have G times V squared or G squared. So this is the famous 1pn, the first GR correction by Einstein, Infield, Hoffman in the 40s. And you can push this to higher order, like the so-called 2pn, 3pn, 4pn, etc. So each vertical row corresponds to a given post-Newtonian order. So here I want to show you that it's actually non-trivial to go from one order to the other. You can see the day where the computation is completed. And even up to date, so far, we only have the complete answer up to 4 p.m. So from one order to the other, usually take several years, and if not like 10 years. And currently, there have been some partial result on 5 and 6 p.m., but we don't have the complete answer yet. So that just show you that the computation is actually complicated because GR is very non-trivial for this perturbation calculation.
Hi, Jiaxian, just to be sure, so 5 p.m. is complete now. According to your...
Because I guess you referred to Damore's paper.
Yeah.
And in his paper, these two are still missing.
Oh, I see.
So yeah, it's 5 and 6 p.m. they're partially calculated, but the 4 p.m. is really the place where everything is known.
Okay, thanks.
Yeah.
The radiation reaction effects will become important at 6.5 pn, is it? Or what is the, at what order they in?
Yes, excellent question. So the radiation effect actually come in at some 4 p.m. order. So to be more specifically, so it come in at the place about in, let me see, in this place.
Is there an easy way to see this counting? I mean, why radiation comes in here? Like from...
Yes. So, okay, I think I can. Good. So what is radiation effect? So basically, radiation effect is I need the binary system to first emit a radiation, and this radiation has to talk to the binary, and then eventually this is absorbed back to the binary system. So we know that the quadrupole moment is a place where you first have the non-trivial radiation, because the 3-point amplitude actually doesn't radiate. So that's the first non-trivial radiation. And in order for this radiation to interact with the binary, you might think that the lowest order would be like this one, where you emit the radiation and then it's absorbed back to this binary system. But this one doesn't contribute to the conservative interaction, because a simple way of saying that is this radiation, they're on shell. So it's differed by a imaginary part. It doesn't contribute to the real part of the amplitude. So in order to have the first non-trivial contribution to the amplitude, the real part of the amplitude, we actually need this diagram. So that means at least this is 3 loop. That's why, so let me back to this. This is 3 loop, so it's actually only coming at order G to the 4th. And this radiation, we will talk about the counting for this radiation mode. And it's actually relatively suppressed by another order of V squared. That's why the radiation, in fact, first start at G to the 4th at order V squared.
Sorry, can you elaborate a little bit about the real and imaginary part? I mean, this was not part of the discussion before. Sorry.
Yes. No, that's good. So let me go back to the first case I mentioned. So a typical propagator, and if it's on shell, that we know the imaginary part correspond to the on-shell piece from this I-pi. So in the potential case, all the potential gravitons, they're off-shell. So therefore, it only contribute to this real part. It doesn't contribute to the cut, which has I-pi. So in the 2-loop case, even though we have this diagram, but the radiation there doesn't contribute to the real part. Actually gives you the imaginary part, which you can think about it like from the optical theorem point of view, that the cut give you the imaginary part. Does that answer?
Okay. Yeah, thanks.
Yeah, I think the simplest way of saying that is from optical theorem, because if this were if this is on shell, then you can place a cut, but that's not what the conservative graviton does. Okay, cool. So
sorry, just one more question. So when you define the classical regime from amplitudes, it was this large impact parameter, like large angular momentum regime, right? Starting from the amplitude.
Correct.
So if I take an amplitude for which impact parameter is not large, is there still a way to quantify the classical limit? I mean, if I have amplitude with extreme mass ratio or something, but the impact parameter is of the order of, say, Schwarzschild radius only, then is there still a way to define the classical, quantify the classical regime in this case?
So when you say the impact parameter is not large,
like of the order of, say, Schwarzschild radius of one one of the masses. So you still have scattering in, let's say, extreme mass ratio or something. But yeah.
I see. That's actually an interesting question. So normally I would say it's not possible.
Right.
But I think there might be one exception. If you take one body to be small,
Right.
like a limit, but the other guy being heavy.
Yes.
In that case, that's maybe possible, but I'm not sure. That's an interesting question.
Okay. Thanks. Yeah.
Yeah, because there's because obviously you can still study.
Yeah, classical, exactly. Yeah. So,
yeah, you can still study geodesic under structural
right.
background. Although, if you're close enough to the structural radius, of course, you don't necessarily get, say, a well-defined scattering angle, as you know, there will be a photon ring.
Yeah, yeah.
So
just outside that range, then.
yeah, there's no like a good asymptotic observable.
Yeah.
That's a good question. Yeah.
Thank you.
Yeah, it's actually an interesting question whether, for example, whether you can discover the photon ring by resuming perturbative amplitude. That's something I actually don't know the answer.
Right.
And it'd be interesting to find out. Okay, yeah, so I guess, yeah, thanks for your question. Those are very good. So back to this PM versus PM discussion. So the PM part, so this 1 PM, 2 PM, 3 PM basically correspond to the tree level 1 loop and 2 loop. And this 2 loop result is the state of on, which my collaborators and I, we now finished last year. And one way to say this post-Minkowskian approximation is we want to do the GR correction, but in the meantime, we want to keep the spatial relativity, or we want to preserve this Lorentz invariance, because we want to resum all the relativistic velocity correction at once. Okay, very good. So I mentioned earlier that the classical limit, the kinematics, and from this point of view, correspond to the forward or the Reggie kinematics. But that's something actually that should ring your bell, because the perturbation in this spatial kinematics is usually very tricky. So let's take a very simple example. So in the tree level, the dominant diagram is given by this G over T. And let's count that what's the next dominating contribution from the 1 loop. So 1 loop, we have G squared. And in the forward limit, all the propagators, they're nearly on shell. So if you do the counting, you'll find out that the T behavior is also 1 for T. But if you remember, I said earlier that the classical expansion parameter is Gm times Q, which is Gm with square root T. That means when I have more powers of G, I should have higher powers in T. But that's obviously not the case for this 1 loop piece. So from this from this tree level piece, if we add up this classical expansion parameter, the corresponding classical diagram is actually this diagram, the triangle diagram. And this one actually scales as G over square root T, which is consistent with this classical counting. So say it differently, this one is supposed to be classical, but the 1 loop contribution, there's a part that's actually more classical than what's supposed to be. And you might find that weird in the very beginning, but a simple way to explain this is from the, say, the WKB approximation, because we have an action like e to I s over h bar. So for order G, we have this linear in the action. But for order G squared, it could come in 2 places. One is that you have the action square that give you G squared, or basically the tree level square part. But there's an order G square correction coming from the action itself. So this is the part that we are interested in, but this part is actually just the lower order iteration. But that would imply that two things. First of all, this loop effect actually contain classical information. So at least when they're in grad school that loops are quantum, it's actually not true. And you can see explicit example here. The second part is that in this very spatial kinematics, the classical part is actually not the leading Reggie limit. It's actually the subleading or more and more subleading when you go to higher and higher order. So in order to find out the correction to the action, that means we need to subtract out this leading divergence. And as usual in field theory, when you subtract something divergent, that usually involves a scheme. So this finite part is actually scheme dependent. So this is actually not surprising because after all, we are studying the correction to the action, and the action by definition depends on the gauge. So you can see from this initial point of view, the gauge dependence coming in from how you subtract this leading divergent part. So this is a place where effective theory becomes very useful because we want to have a well-defined subtraction, and the effective theory will give us control how to define the gauge and remove this divergent part. Okay, so that's what I'm going to talk about next. So we want to construct an effective theory for this bounded binary. And the first question you want to ask when you construct any effective field theory is that what are the degrees of freedom in your infrared limit? So the ingredients here are obviously the two massive particles. And we want to describe this gravitational interaction using the effective action. So that means we don't want to have intermediate graviton in between. So in this sense, this is similar to heavy quark effective field theory, and a little bit similar to soft and collinear effective field theory. So this is the corresponding Lagrangian. We have a scalar field phi correspond to these massive particles. We have a kinetic term whose dispersion relation is given by the usual E squared plus M squared. And the interaction is given by this phi-4 interaction. And what we usually call potential from this point of view is actually the Wilson coefficient in front of this phi-4 interaction. It's actually a little bit different from standard lambda phi-4 because we know the potential, we want a long-range interaction. So the potential is actually not analytic in momentum transfer Q, which will give you a long range when you go to a real space. But that's this effective theory. So you can see that it's very simple. It's basically a phi-4 theory, and all the Venn diagrams are given by these bubble type diagrams. So far it seems very intuitive, but if you recall what we learned in field theory, there's actually something kind of strange here. Because when we first learned effective theory from the Wilsonian point of view, we want to integrate out the heavy stuff. In the IR, we usually have light degrees of freedom or massless particle. But here it's actually like the opposite, because in the effective theory, the remaining degrees of freedom are the massive particles, and we actually integrate out the massless graviton. So how should we understand this? So the way to understand this is from the scaling of the momentum of your gravitons. So this is the so-called potential mode, and in the question earlier we discussed about this a little bit. So basically, this the potential graviton, they're responsible for the intermediate interaction between these two particles, and the wavelength is of the order 1 over r, and the energy is relatively smaller. You can see that from the t parameter, these are purely spatial. So the energy is smaller than the spatial part. So a consequence of this counting is that whenever you see any graviton propagators, we typically have the energy minus spatial elsewhere. but because the energy is smaller than this part, so effectively you can expand these parameters to higher and higher order. But once you do that, because the energy is dt in real space, that means the energy transfer or the time evolution is instantaneous. So when you do a Fourier transform, these are completely local in time. So it means this graviton corresponds to instantaneous potential, which is actually what we want. So you can see from here why we want to integrate out this graviton, because from the time domain point of view, this graviton corresponds to very local instantaneous interaction. So from this point of view, they're ultraviolet. And also because these gravitons, they're never on shell because energy is much smaller than spatial part. So they're off shell, and therefore we need to integrate out this graviton. So on the other hand, the particles, for the massive particles, they're perfectly on shell because the black holes that we can measure that exist there, they're on shell. So what we actually want to integrate out here is the anti-particles for anti-black hole. So you can see that from this effective series setup. So normally for relativistic field theory, the kinetic term is quadratic in time. But here it's only linear in the time derivative. And the reason is exactly because we only want to keep the particle in our EFT, not the anti-particle. If we had the quadratic term in the time derivative, then the energy solution will have both positive and negative, which correspond to particle and anti-particle. That's something that we want here. So that explains why we have this structure for the kinetic term. Okay.
Hi, sorry, can I ask one more question? So till the last slide, you were in the capital G expansion, right? Post-Minkowskian expansion. In the previous, the slide before the EFT slide.
Yes.
And then you said you have to no, the one after this one, the one after this one, the one slide. Yeah, this one. Yeah. So here, and you said that you have to that there's a divergent term, and so EFT matching will help you in. Right, but then this EFT is a non-relativistic EFT that you. Is there an easy way to understand why you are looking at the non-relativistic EFT? I mean,
so you said non-relativistic.
Yeah. The Lagrangian that you are starting with is the.
So this Lagrangian is actually relativistic. For example, in this kinetic term.
Yes.
I put the entire relativistic dispersion relation.
Okay, I see. So it's still a capital G expansion. It's not expansion in V by C.
That's right.
Okay, thanks.
Yeah, and also in this potential, this you can put the entire this coefficient.
Right.
Yeah. Put the entire relativistic coefficient. Yeah.
Okay. Can I ask a question? So the divergent term, does it anyway correspond to this one-point divergence, meaning coming from the self-interaction?
Excellent. Sorry, can you say what type of one-point divergence?
Meaning, if there's a graviton loop in one leg,
Good. Do you mean like this type of?
Yeah, this type of, or like one graviton starting from the one leg and then ending on the same leg. Yeah.
That's good. That's a very good question. So if you, so that's a very good question. So if you do the classical counting I say here, basically on the graviton are very soft, and naively you say some of these diagrams might contribute, and because the graviton is soft, so all the propagators, they're nearly divergent. So that's why this diagram. So at one loop, I don't think they contribute, but when you go to higher and higher loops, you can ask, for example, at 2 loops, why isn't this diagram contribute? And it's actually not obvious if you just use this naive counting from the classical physics. The counting here is more like from this Q over M. So more well-defined counting for why these certain diagrams contribute or not is coming from a so-called massive region. So I will explain later that this, in particular, this diagram, you can see immediately it doesn't contribute because in the classical physics, the gravitons are these potential graviton, they're off shell. So for this graviton loop, there's no place that you can integrate to anything finite. This integration actually gives you 0. But that's something that you cannot see if you just do naive power counting. And I will explain more details later. But the final conclusion is that this graviton loop that corresponds to the RG, the running of G Newton, and that's not classical. And this self-energy diagram, there's not a good physical interpretation, but basically it also integrates to 0. So neither of these two diagrams contribute to the classical limit, the conservative classical limit that we're interested in. Does that answer your question?
Yes. So, I mean, the removal of this divergence is, I mean, is being done by hand, or is there any principle why you should remove the divergence?
So, yes, you will see that concretely how you remove this divergence. So basically, well, let me say the brief words, and I'll tell you more details later. So briefly, this divergence, you can first question ask is that the IR divergence or is that a UV divergence? And because I said that corresponds to a iteration of the lower order event, so those divergence correspond to IR. So what it means is that because it's IR divergence, and because it's IR, so you should see the very same divergence in your EFT. So that's why when you write down your EFT, you should get exactly the same IR divergence. And you will move this divergent part. But the purpose of EFT is give you a precise control about how to control the finite part. Because usually when you move the IR divergence, the problem is not removing the divergence, but having the finite part under control. So that's the part where EFT becomes very useful and give you a well-defined answer. And you'll see concretely how that happens when you go to the 1-2 example.
Okay, thank you.
Okay, so yeah, that's very good because you guys are always asking ahead of me about these good questions. So let me just be very brief about the tree level. So the tree level is quite straightforward. You just basically, we know the leading diagram is given by this T channel exchange, and you glue these 3-point functions together. And that basically give you the corresponding amplitude in your gravitational theory. And the EFT for tree level is quite trivial. It's basically given by this 5-4 interaction. So when you match these two, you can read off what's the corresponding potential in momentum space. And after Fourier transform, that give you the potential in real space. But even from this simple tree level example, you can see a immediate consequence. Because we know the 4-point function only depends on S and T already factored out because that's the counting when we do classical limit. So it means this parameter only depends on S, which is a 1-parameter function. So it means the potential only depends on a single variable. From the 3-dimensional point of view, because we want classical action, the 3-dimensional point of view, this only depends on P squared. So naively, you would say, okay, you have the center of mass momentum P, you have momentum transfer Q, you could have another parameter P dot Q. But for onshore condition, P dot Q is of order, is literally the same as Q squared. So from these 3D kinematics, you can also see that this coefficient only controlled by a single parameter. So this is a one argument, but from classical GR point of view, this is actually not at all obvious. If you look up the literature, we'll find out that the potential usually depends on 2 parameters, this P squared and also this P dot Q over Q squared. So of course, we know for onshore condition, we can simplify this as a number. But sorry, I think number, but this requires do some complicated gauge transformation, but this is something totally transparent from an amplitude point of view. Okay, so tree level is relatively simple. Let me try to discuss some higher orders. So let me first give you a very outline about what are the strategies. So the strategy here is that we have the GR, the full amplitude, and we have the EFT. So starting from GR, we can build on higher dimension, higher result, and from simple tree level building blocks. We will use the double copy to build this tree level amplitudes. So once we have that, then we have the standard generalized unitarity that fusing this tree level result into loop integram. So from the EFT side, it's much easier because these are all the farm diagrams we have. So we simply use farm diagram to calculate the result. And the next is we want to do the integration. We use the same algorithm on both sides that give us the amplitude in full series and EFT. And this EFT, the result will be depending on this unknown and the potential. So this is a function of phi. And when we relate this to amplitude, we can extract what's the corresponding potential. So that's the general strategy that I want to follow here. Okay, so far I haven't mentioned much about amplitude itself. So there are two basic important ingredients we're going to use to build on higher order amplitudes. So the first one is double copy. So let me mention briefly here. So the double copy is that from traditional Einstein-Hilbert action, the 3-point function alone has roughly about 100 terms, and the 4-point function maybe have around like 1,000 terms, and that's very complicated. And this is actually the reason why in classical GR they would like to have the velocity expansion, because if you keep the full relativity result, it's actually quite complicated. However, when we do field theory, one important part of amplitude is the so-called the KLT relation, which is actually coming from string theory. So the statement is that the closed string can be related as the open string square. And in the field theory limit, when we take alpha point equals to 0, that means gravity can be written as the square of Yang-Mills. So one simple example in the 3-point case is that even though we have like 100 turn vertex from Einstein-Hilbert action, when you turn into an unshared 3-point function, it becomes a simple object square. And this is not a coincidence because this simple object is actually the kinematic part of your Yang-Mills 3-point amplitude. So you can see here that this is a Yang-Mills amplitude with a color factor, kinematic factor. When you replace this color factor with kinematic factor, you get the corresponding gravity amplitudes at 3-point. So this is the standard KLT relation. The simplest example is 3-point, and there's a generalization to arbitrary endpoint at tree level. And in this work, we'll actually follow a different formulation of double copy coming from Bernd Carrasco and Johansson around like 10 years ago. So the idea is because Yang-Mills and gravity, they're both local field theory. So we can express the answer in terms of local QB diagram. So these QB diagram, they have the same type of denominator, the propagators. In the case of Yang-Mills, we have the color factors, the kinematic factor. And crucially, the color factors that satisfy Jacobi relation, which is the key that relate different diagrams and realize the gauge invariance. So in order to bootstrap the gravity amplitude, a key insight is that the gauge invariance rely on this Jacobi identity. So if we can massage this numerator to satisfy the same Jacobi identity, then we can place this color factor into kinematic factor, and the resulting amplitude will also preserve this gauge invariance. And now you have two copies, so you live from spin 1 to spin 2. And this is a gravitational amplitude because first it satisfies locality. It's coming from this local diagram, and also it's gauge invariant. Therefore, it describes a gravitational amplitude. So this double copy on the even at tree level will be sufficient for us to build higher order gravitational amplitude. So we first have all these tree level amplitudes here. And from dimension reduction, we can turn the pair of graviton into scalar. So these will be the basic building blocks when we go to higher orders. So now with these tree level amplitudes, when we go to loop level, we'll use the generalized unitarity. And the basic idea is for loop amplitude, the integrand is dictated by the residue of if internal lines become unshelled. And if internal lines become unshelled, these blobs, they become the tree level amplitudes. So by collecting enough tree level amplitude and gluing them together, we can reconstruct what's the corresponding loop integrand. And from this point of view, the BCJ part of the double copy is actually more friendly because it manifests the local propagator structure. So it's more friendly from a unitarity point of view. And one slight comment is that when you square the Yang-Mills part, in 4D, the heuristic is plus and minus. So when you square, you will get extra degrees of freedom correspond to the diatom and the Hsien, because the 2 squared is 4. So only 2 of them are actually Graviton. But you can solve this easy by aligning the heuristic when you do a double copy. Or in general dimension, we can apply the same trick to remove the diatom and Hsien degrees of freedom. So this is the typical generalized unitarity. But what we're interested here are the classical amplitude. So what we want to know is what are the possible classical simplification we can apply in this system. So the first simplification is that because we're interested in long-range interaction, so the two black holes, they cannot touch each other. So for example, like these two, because the two matter lines are touching each other, so these are not allowed. On the other hand, these diagrams, they are allowed for the long-range interaction. The second simplification is that actually the question earlier, that whether we can include these graviton loops or not. So as I explained later, that these you don't have to include because that corresponds to the quantum, the running of your G Newton. So all we want to include is diagram without graviton loops. So that would imply that for each loop, you need at least one matter propagator. And you will see later that when we do the loop integration, these loops actually correspond to the classical phase space. That's why it's still important for classical physics. Okay, so now let's go to the one loop example. Is there any questions so far before I discuss one loop?
So in the KLT, you said that you can do dimension reduction to get the scalars, right, from the pure KLT relations.
Yes.
Yeah, but what if you have spinning black holes? Then how will you?
That's a very good question. So first, it depends what you mean by spin. You can sort of still, so if you're interested in low spin stuff, for example, a spin half, and in that case, because it's still a tree level, so you can play game with, for example, supersymmetry. And you just take supersymmetry Yang-Mills and can double copy. And because at tree level, all the like glulinos, those don't contribute. So that's one way to get you spinning amplitudes. Yes. But that's if you're interested in finite spin, say spin half. But if you say, okay, I'm interested in classical spin, and classical really means the spin is large, not just spin half, but spin like a million. And in that case, it's not that obvious. And so, for example, in the recent paper, what we do is actually we wrote down the higher spin Lagrangian, and we don't have a complete understanding, but at least for 4 point, you can sort of write down a double copy formula for the higher spin amplitude. But that's something we don't have a complete answer yet. Yeah.
And what if you had curved black hole? I mean, I guess in the language of Newton and all. I mean, what if you had a curved black hole, which is like an infinite spin quantum particle, right? So that okay, that also is included in the recent work you are saying that.
So we know 4 point. The answer is yes. You can write down double copy relation, but in general, we don't know. Okay,
even for curved black hole, 4 point is known.
Even for curved black hole, yeah, we don't, yeah, even for curved black hole. Or say differently, for curved black hole, I don't think we have a good answer about what's the corresponding component amplitude. Forget about double copy, even just what's the correct answer for curved black hole. We don't have an answer yet for that, independent of double copy. Okay, very good. So let's go to the non-trivial example at one loop. And as I mentioned earlier, the one loop we want to construct from generalized unitarity. And in principle, there are two different S channel and the T channel unitarity cut. However, we know that this S channel, you're touching these two matter lines. So the information here will not be necessary. So all we need is on the information coming from this T-channel unitarity cut. You can find this unitarity cut because, as I said, even in this unitarity cut, it contains the pure Graviton loop, which is also not necessary. So you can refine this by go to this triangle type diagram. And so this is still straightforward. You can reduce to the standard, say the box triangle integral basis. The next question is, how do you do integration? And we want to develop a method that's scalable to higher orders. So the integration partially is correspond to integrating out this off-shell mode or this off-shell potential Graviton. And the modern approach of doing this is a so-called method region by Benneke and Smirnov. So for potential, it has the scaling, which I mentioned before. And you might wonder that I say Graviton is off-shell, but of course, we detect the gravitational wave. So there must be some Graviton that's on-shell. So the Graviton that's on-shell corresponds to this radiation mode. And a actually more intuitive way to simulate this in GR is that in classical GR, they call this potential mode the near zone because they don't interact with this binary. The radiation mode is what they call far zone because radiation is something that will propagate to infinity. So the wavelength is longer. So this far zone corresponds to this radiation mode. But in the case so far, even at 2 loops, only this potential mode will contribute. So we just need to focus on this part. So for using this potential mode, now we can consider the Graviton and matter propagator. So as I mentioned, the Graviton propagator, the energy is much smaller than 3D momentum. So you can expand them and push them to a numerator. So that implies that there's no energy transfer. So in the time component, that means this is instantaneous. However, for matter, you can't do this anymore. And you'll find out that this matter will generate poles for the Graviton energy. So that's why that's related to a question earlier, why we can't have a diagram with purely just the Graviton loop. Because if you only have Graviton propagator, that means when you integrate the energy, you don't have any pole to localize on this energy integration. because this energy pole, they're only coming from matter. So if you have any pure graviton, the contribution is 0. And for this box diagram, we can see that when we integrate out the energy, it will localize on one of the matter propagator. So you have the remaining graviton propagator and one residual matter propagator. So this is the integral that would actually be IR divergent. And in general, you can have some finite part, even although for this 1D box, the finite part happens to be 0. But this is integral that corresponds to the IR divergence. And of course, in the EFT, we should see the same IR divergence because EFT by design, it describes the same IR physics. So this same integral should also appear in the corresponding EFT diagram, in this diagram. So that's actually EFT. So the key insight here, and this is a question also asked earlier, how do we cancel the divergence? We can see here that this IR divergent integral that should appear with exactly the same coefficient between EFT and full theory. So once we compare between GR and the EFT, so we should see that this IR divergent integral comes with the same coefficient. And so once you equate these two amplitudes, this IR divergence cancel, and this residual finite part, you can use that to fix your higher order potential. So that's how the IR divergence is canceled and how we use the gravity, the full gravitational amplitude to fix the effective potential. So there are two advantages doing this matching approach. The first one is, again, you can see that because we're using on-shell physics, so that will just stand on the minimal degree of freedom. The potential is still a single parameter function, depending on p squared. The second part is that normally in GR, different people, they can choose different gauges, and the potential is not well defined. In order to relate different potential, what you have to do is to do the so-called canonical transformation. That's not something we learn in undergrad mechanics. But it's actually complicated to do canonical transformation because you have to make an ansatz and you try to solve this Poisson bracket. On the other hand, a more invariant way to calculate to see whether two potentials are equal or not is actually to compute the corresponding amplitude. Because if they correspond to the same amplitude, that means these two potentials are equivalent. So that gives you a very efficient way to compare two gauge-dependent potential through a gauge invariant amplitude. Very good. So now let me briefly discuss the state of one order G cube result. Is there any question before I move on?
Sorry, can you explain the gauge invariant potential part again? The last thing that you said.
On the potentials, as usual, they are gauge dependent. So that's why comparing two potentials are very difficult, because they can look very different, and yet they describe the same physics. Just like the action itself is not can be different, but describing the same physics. So an efficient way to comparing two different potentials is actually calculating the corresponding amplitude. Because once you get to the amplitude, they're gauge invariant. So the answer, if they're the same, then they are the same. If they're not the same, then they're definitely two inequivalent potential.
But once you go from the, I guess, MEFT to V, because you want to compare with the post-Newtonian potential expansion, so that you have to compare in a particular gauge for V, right? I mean, the final answer that you want is for the potential, I guess, right? In some gauge. I mean, if you want to compare with the...
So yes, so what I would do is, instead of just comparing the potential, I would take the potential in the literature and calculate from their potential what is the corresponding amplitude. And I would compare at the amplitude level.
Okay, thanks.
Yeah, there's some technical details about you have to be careful when you calculate amplitude, but we can discuss that after.
Okay.
So for order G cube, these are, so for one loop, the only necessary unitarity cuts are the triangle cuts. So for two loop, the corresponding unitarity cuts are these three. So again, they satisfy the same principles that these two matter lines, they're always separated by these gravitons. And also for two loop, there's two matter propagators on shell. So all the lines here you see are on shell. And the blobs here is correspond to the amplitude. So for example, this is a 4-point Graviton amplitude that has STU diagrams. And once we have these unitarity cuts, we basically feed through the same pipeline. And for example, for this unitarity cut, you can see that it's very compact. And there's some residual double copy structure coming because it's kind of small, but this E and O square are the even and odd parity part. That is actually the same ingredient coming from the Yang-Mills unitarity cut. So once you have this unitarity cut, you can merge it into integrand and do the same integration strategy. And this is the corresponding answer for order G squared, and order G cubed. So from here you can see that the tree-level part is trivial because only tree level. The one-loop part is still very simple, but the two-loop part is actually where interesting things happen. So one very interesting thing that I want to mention is that this new parameter, the new here, actually correspond to the reduced mass ratio, M1 M2 over M1 plus M2 squared. So these new parameter, they first appear inhomogeneously at order 2 loop. But for 3 and 1 loop, they doesn't show up. They are overall just new factors. And why is this interesting? Because that corresponds to the check that we can do. So one check you can do is to go to the so-called probe limit, where you take one particle to be very heavy and the other particle to be very light. In this limit, you can use the geodesic equation in Schwarzschild limit. And there's actually a Hamiltonian that's known for order in G in this limit. So you can see here that the 3 and 1 loop, they're relatively simple because they're entirely fixed by this Schwarzschild limit. However, for 2 loop, it's actually not the case because for this new dependent term, we can fix them using just the Schwarzschild limit. In particular, there's a very interesting Rc function that appear. With this Rc function, they appear with this new vector. So it corresponds to the first the small mass correction in this port limit. And this is actually a very interesting direction because that's another overlap with a different community that's called self-force community. So what they basically do is they study a small pole particle under a Schwarzschild background, but they want to include the back reaction from the small particle to the Schwarzschild background. And the back reaction is controlled by this mass ratio nu. So this will be the correction from this self-force correction. The second check we can do is to compare with existing GR potential. So at the time we wrote the paper, the available ones were this 4 p.m. So the available overlap we have is order 1, order V squared, and order V to the fourth. So this is related to what I said earlier. So to compare two different potentials, as you can see here, they look quite different from what I showed earlier. In particular, you have lots of very large rational numbers. And if you look closely, they're actually a pi square, they appear in their answer, which is not even rational. So they look very different, and yet when you compute the scattering amplitude, they give you exactly the same amplitude at order up to order V to the fourth. So that shows you that the potential we got and the existing classical GR result are completely consistent in this overlapping region. So once we validate our result, the question is whether this is something that LIGO people are interested in. And at least some of them are interested in what we're doing. And they put out a paper a week after our result. So this is what they tried in order for the application of LIGO. So once we hand you the effective Hamiltonian, now you can study the bouncy easily by plugging classical equations motion. So one thing you can do is to study what's the binding energy as a function of orbital frequency omega. So what this plot does is to plot this binding energy as a function of omega, the horizontal axis. So the frequency, when you go higher and higher, that corresponds to the later stage about your merger, about your in-spiral phase. So you can see that all the predictions are relatively agree with each other initially, but so in the end, they start to deviate from each other. And these light blue lines are the result from numerical relativity, which you can take as the truth. And these different lines, they are different theoretical models. So the closer you are to this light blue line, then it means you're closer to the quote-unquote truth from general relativity. And this dashed line in this scenario is the closest one to numerical relativity, which is based on our 3PM Hamiltonian. So this is still a, I think it's fair to say, still relatively preliminary, but at least that shows you that part of the LIGO people are interested in what we are doing. Okay, perfect. So I think
so the post-Newtonian expansion is done at the end of the amplitude computation. Is that correct? You compute, say, the two-loop amplitude, and then you do the post-Newtonian.
You mean this part?
The other one before, yeah. The answer you had written for M3, I think.
Exactly. Yes. So
that's a relativistic answer, and you do expansion of that in B by C to compare with the.
So actually, in the paper, when we wrote the paper, the integration method is actually doing order by order in V expansion. Okay. And the technical reason why we do that is for those three-dimensional integral, we can't do that unless we do velocity expansion. Because if you don't expand, then you don't get, the integrals you have are not standard Feynman integrals. So for that technical reason, we do the velocity expansion at the very last stage of our computation. So the original result we have is actually V expansion up to 7p and order. But you can see the pattern very obviously, such that we can resum to order in velocity.
Right.
And the key to do that is actually coming from the amplitude side because we're starting from amplitude, so the results are just one parameter function. If we hadn't done that, then it could have been some complicated function which we don't know how to resum. But because we're starting from amplitude, so the structure, it becomes from two parameter function become the one parameter function. That's why resumming is so much easier.
But the final answer is a resummed answer at, say, 3 p.m., 3 post Minkowskian order, right? So then if you take the final answer and you expand it in V by C, yes. And if you look at now this table that you have, then at the row corresponding to 3 p.m., we know like all terms in Pn expansion, right? For that, I mean like 6 p.m., 7 p.m., all the terms which are, say, 3 p.m., npn, like all those terms are known now. Is that correct? Like if,
you mean, yeah.
Yeah,
so
but like,
right. A, V to a 10.
Yeah,
they're
exactly.
They're all given by the relativist expression shown in this result. So the sigma here is equal to P1, relativistic P1 dot P2 over M1, M2. So this is a relativistic expression.
So one knows a lot more in PN expansion now than even more than 6PN, I guess, right? 5PN at least.
Yeah. So the PN direct PN result is known up to 6PN.
Right, but using your result, we can go higher at 3PM at least.
Correct.
Yeah. Thanks.
And I should say that there's a recent paper by Rafael Porto, Gregor Kalin, and I think Leo, and one of their collaborators, they also verify our result and to order in velocity expression.
Okay, thank you.
Yeah. So that paper just came out very recently, maybe like only a few weeks ago. But that's I would say, a first independent calculation that gives order in velocity, because other Newtonian result is only fixed order in V. Yeah.
Question. So just regarding this plot. So can one say that at higher, the plot that you have to compare with the numerical simulation. So is that fair to say that at higher angular velocity, the PM expansion is actually better than the PN expansion because of the fact that the PM expansion seems to give the closer answer compared to the PN?
Yeah, so that's the part that could be very model dependent. And notice that this Hamiltonian, they are not exactly our 3PN Hamiltonian, but they're 3PN Hamiltonian, after this EOB model. But there are also free parameters in the EOB model. So the question is, in this particular result, the data taking our 3PM happen to works the best compared to numerical relativity. But in other scenario, this might not be the case. And this also depends on how you exactly do your EOB mapping. So I would say it's not conclusive yet, at least.
I see. So the other plot, so the other lines, do they correspond to taking PN results into
Yes.
and using the same model?
The solid lines, they use the PN inputs. Is that what you're asking?
Yeah, basically the difference between the various lines. Yeah.
Yeah, and also like these dashed lines, they also use PN. But the one big uncertainty is how exactly do they do the EOB mapping? And
I see. But within a given EOB mapping, it's the PM that is giving the closer result than the PN expansion.
I think it might be the opposite, but I'm not entirely sure. It might be the opposite, that PN for a given EOB mapping, the existing so far the post-Newtonian one might still perform better than post-Minkowskian.
But isn't this showing your post-Minkowskian performing better? Sorry, maybe I'm.
So there are other plots. So this is one of the plots in their paper. There are other plots where the conclusion is the opposite. That's why I say it's still preliminary, because it heavily depends on what your inputs. And also one big assumption here is that, notice when I say how you compute this diagram, you only use the conservative Hamiltonian. So namely, in this particular plot, they don't include the radiation, in fact. So what they do is actually they just calculate the binding energy for different orbital frequency. And effectively, they treat this as adiabatic. There's no real quadrupole radiation combined with this one. So there, as far as I can tell, there are a lot of moving parts into what's the actual conclusion. So I would say it's at least not conclusive yet.
Okay. All right. Thanks.
Yeah.
Yeah. Hi.
So,
sorry. Yeah. Just one more question. So this table somehow implicitly it looked. The table is such that the PN and the PM expansions are kind of independent, right? I can look at 3PM and go to NPN.
Yes.
But as you explained in the beginning, for in spiral, I mean, they are not independent expansions.
Good. Excellent. So, very good. So, for example, you can say from our 3 p.m. result, if I just want to use that alone and calculate the binding energy, then if you use that, then all you can say is only accurate up to 2 p.m. if you use this G cube result alone. Because you can get this higher order, but you can get the contribution from that, but it's not gauge invariant because you're missing this higher orders. You're missing this part.
Right.
But on the other hand, this is still useful because when the post-Newtonian people, when they calculate like 5, 6, 7 p.m., etc., at least there's a definitely prediction about a fixed G order, what's the corresponding potential.
I see.
Right. So saying differently, these PN only become absolutely relevant when you compute the circular orbit. But at level of Hamiltonian, you can still separate these two effects.
Okay, thanks.
Good. So I think I'm reaching the end of my time. So I think I might just skip spin. You can more than welcome to ask me afterwards. But I think the goal today is to show that this that new direction in the amplitudes community really is trying to simplifying or solving GR. And the particular approach here is how do we start from amplitude, go to gravitational waves or bound states. The connection might not be very obvious, but one very simple approach and straightforward is that we go to the effective theory, and that allows us to connect the beauty of onshore physics and also like real physical bounded system of gravitational binaries. So I just want to mention about future works. So one obvious future work is that we first see the non-trivial result at order G cube. So obviously you want to understand what's higher order. And one particular thing that's interesting is that these two are the place where this the so-called first cell force or the first like the reduced mass ratio order 1, the reduced mass ratio nu first appears. So that's something independent that you can study at this order. And also at this one, order G to a force, that's the radiation reaction first appear. So we can also study what's the radiation reaction in a relativistic way. And once we have that, then a very ambitious question is, can we try to resum both in velocity and G Newton? So far we're able to resum in the velocity, but once we have enough result from over the G Newton expansion, we might be possible to get strong gravitational regime by resuming if we see any pattern. So the second future direction is the amplitude program really give us a chance studying the hidden structure about classical gravity. So for example, a very interesting development so far is the double copy relation, especially on this work, for example, by Donald O'Connell and his collaborators on the space-time structure using double copy ideas. And another thing which is, for example, Yuting is the one discovered with his collaborators and also like Barnes, Carrara, and Osherov, that the curved black hole corresponds to the minimal spin. But we don't fully understand this even at a level of G squared or the computed amplitude. So that'd be something also interesting. And on top of spin, of course, you can study radiation. And another interesting direction is how does supersymmetry help us? And one recently interesting result is that the pure gravity in the Eskimo supersymmetric gravity, they actually correspond to the same result in the high energy limit. So maybe you can gain some insight from supersymmetry. So they're more like remotely ideas, which is, can we use the simplicity in amplitude and bring that into some simplicity and bound state and maybe even more to quasi-normal modes. But those are more speculative ideas. And to solve this bound state, we see a systematic approach is to go to effective potential. But as I mentioned in the very beginning, an interesting part is we can study resumming the amplitude and directly study the bound state from the emerger and pole structure. So the question is, can we pursue this direct approach and study bound state directly from amplitudes? So, okay, with that, I'll conclude. So thank you very much.
Okay, thanks, Jia-Hsien, for the very nice talk. Let's see if we have any, so if you have questions, raise your hand, or you can just unmute yourself.
Yeah, so one more thing I just wanted to ask was the EFT that you work with was for elastic scattering, right?
Right.
Is there any development if you have inelastic scattering like radiation emitted, for example? Is there a EFT?
So far, no. But that's something we've been having in mind. Yeah, because the discussion here, we only use conservative Graviton or the potential Graviton. That's why the EFT is sufficient to just use the conservative potential part. But of course, the very natural question is, how do you include radiation? In fact, yeah, and that's definitely something very interesting to figure out.
Sorry, just to interrupt, the EFT part of that story is known, right? The radiation, when you talk about radiation reaction, the EFT part is known. But you're
Yes.
saying how to use that to get maybe the.
So definitely, what's known in the radiation part
Yeah.
is how to connect from EFT to gravitational waves. That's absolutely, as you said, is known. And for example, like Goldberger and Andy Ross.
Right.
What's not obvious is actually how to start from amplitude and connect to the EFT.
Mm-hmm.
That's the part that's not obvious. Once you have the EFT, then you can just do a usual thing and bring to the classical gravitational waves.
Right.
Oh, I see. So sorry. So my question was that the EFT that you wrote down, I mean, the kind of from the heavy quark effective field theory type motivation, right? The one that you had, is it directly related to the Goldberger? I mean, can that EFT be generalized if you have radiation, for example? The one that the Lagrangian that you wrote down.
So,
which had the potential, which had the expansion, right?
Right.
Yeah, exactly. Yeah, this one.
So I would say so far the answer is I don't know.
Okay, yeah, I see.
It's not done. It has not done, but it's definitely something very interesting to study.
So just a curiosity, is there an EFT for the quasi-normal modes?
I don't know. Yeah. The question is what, because yeah, I don't know. Yeah.
Okay, all right, thanks.
Yeah. So the only thing.
Just wondering, yeah.
I have a question.
Yes, please.
So, in recent the Moore's paper, where he computed the 6PN, so he mentioned this non-local in time terms in the contribution to the scattering angle.
Yes.
So, how do these non-local in time terms enter in the amplitude approach?
Are you asking about the paper that appeared last night?
Yeah. Well, I mean, in general.
Yes.
You have non-local in time contributions, right? So how do they like enter in the amplitude computation?
That's something very interesting, which I always want to know, but I don't really have an answer. So my speculation is that, well, first, we know how to calculate the angle with the conservative potential, and that's very straightforward. You just use classical mechanics. But what I don't know is once you have dynamical radiation, how would you include this effect in your classical equation of motion? So that part, I don't know, and there's probably some well-known approach. An alternative way to do that is, the approach from Donald Connell and David Kasawa and Ben Maybe. They wrote down how to calculate the scattering angle directly from amplitude, and which doesn't rely on EFT. And my speculation is that maybe that formalism is very ideal for this purpose, because once I fit in the full amplitude with the radiation effect, and I can plug into their formalism, and presumably that will give you the result including radiation effect, because the inputs there contain both onshore and offshore graviton. But yeah, that's my speculation, but I don't know.
I see. Okay, thank you.
I have a question. So you mentioned that there is one metal line on shell in every loop.
Yes.
But we usually don't demand that condition, and just do a double. So for example, in the one loop case, we just do a double cut on the Graviton line. So
yes.
If we just calculate it without demanding the metal line on shell, will we get the same answer?
Yes. So you will get the same answer. Let me go back to. Yes. So you can say, for example, I can say I can start from this, let me go A, or I can start from this, let me go B. So of course, if I compute the full amplitude, the answer from A and B will be different. And one obvious example is that the B contains this Graviton loop, which you don't have in your input A. But crucially here, we don't have to calculate this diagram, because this diagram in the classical limit, or more precisely in the case of potential graviton, is actually 0. So in this limit, the A and B give you the same answer. But but the advantage that we can go to use one metal line on shell is that because when you cut more and more lines, the answer becomes more and more simpler. So that's why we know A and B give you the same answer, and because of that, we can take advantage and use the A, this triangle cut, because they're simpler than the bubble. Then just cutting to metal line instead of cutting the three lines.
Makes sense.
Yeah, sure.
Okay, is there any further questions? Just in the chat. Okay, great. Okay, all right, thanks. I think this is probably the end. So let's give a round of applause to Chia-Hsien for this very nice talk. And mute.
Thank you, everyone.
All right, thanks, Chia-Hsien.
Yeah.